Okay, section 2.2, parent functions and transformations. The essential question, what is a parent function? How do we apply transformations to parent functions? So that's really what we're looking at in this section. So there is a collection here of parent functions, and we're going to be looking at how we can determine from an equation whether it should be shifted left, right, up, down, whether it should be stretched or shrunk or reflected. And as we're going through these, we're going to, most of this I'm sure you have seen before. As we draw these graphs that correspond with these functions, just know that you're expected to be able to associate the graphs with the original equations. So for example, the first one, the linear function, is, and I'm sorry, I think I forgot to read this up here. The parent functions, the definition of a parent function is the simplest function of a family of functions. Okay, and with a linear function, we have the equation f of x equal x. I know that's linear because it's not being raised to a second or a third power. There's no square roots involved. There's no exponents. All right, and then this is just a basic straight line passing straight through the origin. So it looks just like this. Okay, so everything that's going on this sheet, these are things that you're responsible for, that you should be able to remember moving forward. We're also going to talk about the domain and the range. So we talked about domain in the previous section. Domain is all possible x values moving from the left to the right of this graph. All right, this thing goes forever in both directions, so we're going to say it has domain negative infinity, positive infinity. And when you're doing interval notation, anytime you have infinity symbols, you will always have these round parentheses with them. We're going to also do our range. Our range is the y values, so you're going to look at that from your lowest to your highest points on your graph. And because these have arrows, they go in both directions forever. So the range is negative infinity to positive infinity. Okay. Then we have the absolute value function. So the equation is f of x equals absolute value of x. This one is a V shape centered at the origin. So the right side of it is identical to the linear function. It's exactly the same on the positive side of all the positive x values. So it's going to go through, we're going to draw it through 0, 0, 1, 1, 2, 2, 3, 3, etc. All right, but on the left side, it's not going to go down into the negatives, rather it's going to stay up above the x-axis. So now it's going to go through this way. It's still going to go through all the integer ordered pairs. So it's going to look like this. So just remember, absolute value graphs have a V shape. The domain is going to be all the x's, negative infinity, positive infinity. The range is all the y's, starts at 0, goes up to positive infinity. I'll put a square bracket at 0 because 0 is part of the range. Parentheses on the infinity. All right, then we have the quadratic function. That one is f of x equals x squared. This one is always going to be a parabola shape. Okay, so it's going to be a U shape centered at the origin. So it's going to look like this on one side and this on the other side. The domain, x values are going to, it begins at negative infinity on the left, it goes to positive infinity on the right. And then my range, my lowest point is at the origin, so y equals 0 all the way to positive infinity. My square root function, f of x equals the square root of x. Okay, this graph is going to look like a parabola lying on its side. Now, of course, if you're not seeing how to get any of these, you can always do a table of values. You do your x, y table, put in some numbers, and see what you get for your y values. So if I put in 0, 1, 4, I can see that if I put in 0 for x, it's going to give me 0 for y. Put in 1 for x, the square root of 1 is 1. Put in 4 for x, square root of 4 is 2. So I've got order pair 0, 0, 1, 1, and order pair 4, 2 is here. And if I do it on the calculator, I'll go to the y equals feature, and I'm just going to type in square root x, so second square root x, and I'm going to graph. And I can see the shape that I need. It looks like a parabola lying on its side, but it's only the top half. So this is my square root function. My domain for this one is going to go from 0 on x to positive infinity. My range, from bottom up, it starts at the origin, it goes up to positive infinity. Okay, so that's my square root function. Then we've got our cubic function. All right, so cubic, that means you're raising it to the, you're going to do x to the third power. Okay, so let's look at a table of values for this. Let's see. No, I'm going to put in, technically you can put in anything that you want for x, but I'm going to put in numbers that are going to give me easy things to work with. Since I'm doing a cubic function, I'm going to put in values, I'm just going to put in numbers that are close to 0. These are usually a good place to start. If I put in -2 for x, -2 to the third power gives me -8. -1 to the third, that gives me -1. 0 to the third is 0, 1 to the third is 1, 2 to the third is 8. So if I plot my points over here, -2, -8. So I kind of had to eyeball some of that. Order pair -1, -1 is here. Order pair 0, 0, +1, +1, and +2, +8. So it's going to be about right here. And if I put this into the calculator, I'm going to do x raised to the third graph. And I can see I've got it's like a parabola on one side, but it got flipped upside down on the other. So this is your x cubed function. Looks like this. Now it looks really steep, but it does not turn, it will never turn into a vertical line. It's just a really steep graph. Okay, so for my domain, left to right, it does gradually spread out. So it's going to go -infinity to -infinity. I'm sorry, -infinity, +infinity. So I meant to say. And for my range is a little easier to see. It goes down forever, up forever. So -infinity, +infinity. Okay. Then we have our cube root function. So it looks like f of x equal cube root of x. Okay, so we'll do a little table of values. Ooh, I didn't mean to put it there though. I'll put it in the margin. Okay, so I can put in a table of values for this one. Let's see what I get. All right, now this time I'm gonna, you can always put in anything you want for x for a function and just see what you get for y. But I'm gonna be smart about this. I'm gonna put in perfect cubes so I get results that are easy to graph. So I know that 8 is a perfect cube, so I'm gonna put in 8. And I know that 1 is a perfect cube, so I'm gonna use that one. And I'm gonna use 0, I'm gonna use -1, and I'm gonna use -8. If I put in 8 for x, cube root of x is going to give me 2. And then put in 1 for x, cube root of 1 is 1. Cube root of 0, 0. Cube root of negative 1 is negative 1. Cube root of negative 8 is negative 2. So if I find these points on my graph, I've got 8, 2, about here, like this. And then 1, 1, 0, 0, negative 1, negative 1, and negative 8, negative 2. So right here. And this one, if I put it into the calculator, I'll see my graph is going to take this shape. All right, and just like the previous one never turned into vertical lines, this one will not turn into horizontal lines. They just get really, really shallow. Now for my domain, it's negative infinity, positive infinity. And my range, even though it's really shallow, it's still going to be negative infinity, positive infinity. Okay, so that's the first part. Got a couple more functions to kind of explore before we go on to the transformations next. All right, we've got one called the reciprocal function. Okay, this one is f of x equal the reciprocal of x, so 1 over x. Okay, and we can do a table of values on this one as well, and I'm going to go onto the calculator and go ahead and type it in. We want to do 1 divided by x, and I need to get my exponent out. Okay, graph. Oops, I'm going to try it again. One divided by x and graph. Okay, so what have we got here? Basically, what we have is a shape that looks like this in the first quadrant, and then it's shaped like this in the third quadrant. Okay, it's also, you'll notice that since x is in the denominator, x can never equal 0, because if it did, that would be undefined, because remember, you cannot divide by 0. Okay, so for our domain, the domain is going to, I'm going to add in here x cannot equal 0. So the domain is going to go from negative infinity all the way up to here when it cannot touch this line. So the domain is negative infinity to 0. Because it cannot actually equal 0, I'm going to put round parentheses, union, and then I'm going to pick up on this side from 0 to positive infinity. My range is going to go from my lowest point, so negative infinity, up to the x-axis, but it does not actually touch the x-axis. So 0, parentheses, union, parentheses, 0, positive infinity. Okay, and if you want to see why it works out that way, just make up a t-table on the side, put in some x values and see what you get for your y's, and you'll find that it's following this pattern that we've drawn. And then the last one that we're going to talk about is the greatest integer function. Okay, this one is defined to mean the greatest integer that is, the greatest integer that is less than or equal to x. And then we're going to write f of x equals, and we're going to draw it like this. It's got these symbols, these little square brackets to indicate greatest integer function. The way this one's going to look is, we'll do a t-table this time. So let's say if I put in a 4 for x, then the greatest integer less than or equal to 4 is 4. What if I put in 3.5? The greatest integer less than or equal to 3.5 would be 3. What if I put 3.2? The greatest integer less than or equal to 3.2 is also 3. If I put in 3, the greatest integer less than or equal to 3 is 3. If I did 2.5, the greatest integer less than or equal to 2.5 would be 2. So you'll see you're only getting whole numbers in your y column. When y is 2, or excuse me, when x is 2, y is 2. So we can graph this. We can go to 4 on x, 4 on y, and put a dot. 3.5 on x, and go up to 3 on y. That's going to be on there. 3.2 on x, and then 3 on y. And if x is 3, y is 3. So what's happening is you're filling in all these spaces in between, but when you get to the next integer, when x becomes 4, it jumps up. So we'll put an open circle to indicate that it's not actually defined at that point because it's going to jump up to the next level, like this. As I move down, if x equals 2.5, then y is equal to 2. If x equals 2, y equals 2. So it's going to fill in here, but it's going to be an open circle here. Some people call this a step function. And then you can fill it in to continue the pattern. So it's going to be a straight line and then an open circle at the integer. Straight line, open circle at the integer. And it goes all the way back. Okay, so that's what that one looks like. And you can fill it in all the way down. And we're not going to worry with domain and range on this one. Actually, domain actually is going to be all real numbers because every x does eventually get included. So I said we're not going to worry with it, but I'll give it to you anyway. Domain is all real numbers, negative infinity, positive infinity. The range, however, the y values, is only going to be the actual integers. So it would be the set, I would do ... -3, -2, -1. It would be all the integers. But I'm not going to ask you to give the domain and the range for the step for the greatest integer function. All right, and now let's talk about our transformations. So with transformations, we can explain this is how a graph has been moved or the shape has been manipulated. Okay. All right, and then this is our standard form for our transformations of any function that's been transformed. So this f of x, all this notation is really based on the equation y equal f of x. Okay, the different letters have different meaning. The a in the front, this tells us if there's been any type of vertical shift or vertical shrink. So the a value determines whether the graph has vertically, I'm going to say, stretch or shrink. I know it's not perfect grammar. Stretch or shrink. H, all right, this tells us if the graph has been translated left or right. Okay, so this is left or right. And this is something that I know that you've been doing for the last couple of years, so it shouldn't be new. K, the K value determines whether the graph has shifted up or down. A negative f of x, that would be like a negative, and like for example, if you had y equal negative absolute value of x, a negative in front of the entire function is a reflection across the x-axis. Let's just play with this. Let's go into the calculator, and if we go to y equals, and I'm going to graph the I forgot how to graph the absolute value of x. I may have to play with that a little bit and come back to it. Instead of doing absolute value of x, let's do square root of x, because I remember how to type that one in. Okay, so if we do y equals square root x, so second square root x, and then for my second, so let's graph that one first. We know that the square root of x has that shape. All right, now let's do a negative in front of it and see how it changes it. So now I'm going to clear that one out, and I'm going to say negative second square root x and graph that. Okay, the negative in front of the square root function, it flipped it across the x-axis. That's always going to happen if you have a negative, if you multiply the whole function by a -1, it's going to flip it across the x-axis. So negative f of x demonstrates a reflection across the x-axis. F of negative x, so if we change the signs on all the x's in the original graph, that is going to flip it across the y-axis. Okay, and just look at the picture. Look at the picture up here for a second. If you took, let's say if you had x equal 3 on here, the original, but we changed it to a -3, it would bring it over here. And then all of these, if we change the signs on the x's, it would bring them over here. So f of negative x demonstrates a reflection across the y-axis. So that was x, and this is y. Okay, and now let's look at some examples. So the directions state the parent function and the types of transformations, then graph the parent function and the transformed function on the graph below. So number 1, all right, so how do we determine what type of function we have here? I don't have the paper to look at, and it's not easy for me. Let's flip it over for a second, though. Let's just look at some of the characteristics of all of these graphs and your equations. So this is x to the first, this is the absolute value of x squared, square root of x. Those are the things that you're looking for. Here's an x cubed down here. Okay. So in examples 1 through 3, what do you see? In example 1, I see a square. So that tells me it's some transformation of the x squared function. So I can say it's the x squared function, and I don't have much space here, but it's the x squared function. All right, and then what types of transformations are going on? Well, the -3 inside is the shift 3 units to the right. Okay, now that probably seems confusing at first, but the horizontal shifts are always going to be backwards from what you would expect them to be. If I go to my calculator again, all right, so I did square root of x before, and remember it was started at the origin. But what if I typed in second square root of x minus 3? And then graphed it. All right, the -3 inside the square root function, it shifted it 3 units to the right. So even though I subtracted 3, it moved it 3 to the right. So those horizontal ones are going to seem backwards. The +2 out here is a vertical shift, 2 units up. So the vertical ones are intuitive, they make sense, 2 units up. Okay, so if I've got the x squared function, I'm going to actually draw the original like this. And then it was transformed 3 units to the right. Okay, so now it's over here. Okay, so it went over 1, 2, 3 spaces. And now the +2 is going to move it 2 units up. Okay, so I'm going to start here. I'm going to go up 1, 2. So my final answer is the red graph. Okay, so the red is the final answer. For example 2, what parent function do I have this time? I see absolute value bars. All right, so we've got the absolute value, y equal absolute value of x. So let's draw that first. It's a V shape. All right, the inside I have a -3, so just like in example 1, that's another horizontal shift, and it moves to the right 3 spaces. Okay, and then it also has a negative on the outside, so that is going to be a reflection across the x-axis. It's going to turn the whole thing upside down. So my final answer is my red one. So that's what the final answer looks like. And I forgot to state the, see, I stated the parent function and the types of transformations. So we had a horizontal translation, and we had a reflection across the x-axis for number 2. I know this is all crammed in here mighty tight. Okay, and then for number 3, y equal 3 to the x plus 1 power. So this is the exponential function, and I don't remember us talking about exponential functions. Did we do that? I don't think it was on your sheet. That's another important one that you do need to know. All right, so let's go back to flip back to the front page, and we need to include that one. Go to the very bottom, the exponential function. Okay, the exponential function is the equation f of x equal a to the x power. And if we do a table of values for this one, we would find that it looks like the following graph. We're going to do I'm going to do 2 to the x power. I could do any base, 2 to the x. 2 raised to the x power graph. Okay, so the exponential function is this swoosh like shape, and it's going to pass through 0, 1 on the y-axis, but it's not going to ever touch the x-axis. So it's actually going to look like this. It's going to touch at 1, and it's going to be shaped like this. It's going to come back like this, but it'll never actually touch the x-axis. Okay, now I know you're going to be responsible for this graph, but I don't know if you will be just now or if that's going to be coming later. But that's what the exponential function, or the graph of the exponential function, looks like. So if we go back over here, because we have that variable in the exponent, then we can see that it's that function that we just graphed. And I'll put it back over here again. This is the original exponential function, with that y-intercept right there at 1. And this plus 1 up here is a horizontal translation, just like you had back here with the 3's. It was inside the function, so here it was inside the base, and it was inside the absolute value. Now it's inside the exponent, because this is an exponential function. So we're adding 1 to the x, and that's going to shift it 1 space to the left. So this point's going to come back here, and then the graph is going to look like this. And it still can't touch the x-axis. So that's the final answer there. So that was the exponential function. And it was shifted 1 unit left. All right, and then we've got a couple more examples to look at. Okay, so here, write the equation of the function with the given transformations. All right, so A, we have a quadratic function. So I'm going to do this in parts. Quadratic means it's going to be f of x equals x squared. It's reflected across the x-axis, so that means that I'm going to make the entire function negative. Let's see, let's do it. Let me kind of try to organize this a little bit better. Okay, so the reflection across the x-axis is going to make it f of x equal negative x squared. All right, left 3 is going to add 3 to the x. So f of x equals negative, I'm going to use parentheses, and I need to add 3 to my x because it's going to the left. And then down 2, I'm going to add 2 to the end of it. So it's going to become f of x equals negative, oh, I forgot my square. Negative, parentheses, x plus 3 square, and then down 2 is going to be minus 2. So that's going to be the final answer. Okay, part B. We have an absolute value function. Okay, reflected across the y-axis, that's going to put a negative in front of the whole function. So it's going to become f of x equals negative absolute value x. A vertical stretch by 8 is going to multiply 8 to the whole function. So we're going to wind up with f of x equal negative 8 times the absolute value of x. All right, and then finally square root function, so f of x equals square root x. We're going to go right 7. So it'll be f of x equal square root of x. Because I'm moving to the right, I'm either going to, because it's a horizontal shift, I'm either going to add or subtract from my x inside the square root. If it's going to the right, then I have to subtract 7. Remember, it seems backwards. Up 9, that's going to be plus 9 after it. Okay, so this means you're going to do f of x equals square root of x minus 7, but on the outside, you're going to add 9 to indicate it goes up. And then finally, we've got a vertical compression of 1/2. So we're going to multiply the whole thing by 1/2. F of x equals 1/2 times square root x minus 7 plus 9. So since this was the last step, it's going to get applied to everything we had done up to this point. Okay, and that's it.